Hello, everyone. Welcome back. We are going to start our journey into Chapter 13, which is on the details of the glass transition and relaxation behavior. We have three lectures in Chapter 13. This first one is meant to be kind of an introduction and a bit of a deep dive into the physics of the glass transition. We've discussed this a bit throughout the course, and today we are going to dive in a bit deeper about what are some of the implications of the glass transition from the perspective of fundamental physics. Now, one of the things that we know about glass is that it is a non-equilibrium material, and there are a lot of consequences of glass being a non-equilibrium material, including the fact that its entire thermal history influences both its microstate and its macrostate. But the question arises, what is equilibrium? There are many different definitions of equilibrium, different criteria for equilibrium under different conditions. And one of the ones that I particularly enjoy is due to Feynman, who said, equilibrium is, quote, when all the fast things have happened, but the slow things have not. And this begs the question, what is fast and what is slow? This definition of fast and slow really depends on your perspective as an observer or as the person doing the experiment. For example, let us consider a cup of coffee with some cream poured in it in a cup in a room. Um, Once we pour the cream into the cup of coffee, there is a chemical equilibrium that is reached as it homogenizes. But if we wait a longer period of time, the hot coffee cream mixture will reach a temperature equilibrium with the room. And if we wait an even longer period of time, it will reach a vapor equilibrium with the room, and all that will be left is this little ring of what used to be coffee at the bottom. Which one of these is the true equilibrium? The answer is it really depends on you as an observer and what it is that you care about in terms of what you're studying. If your goal is to study the hot coffee cream mixture or the approach to chemical equilibrium, then this first equilibrium is the relevant one. This is an equilibration that occurs on the time scale of seconds. Or if you care about heat transfer, then the temperature equilibrium would be the relevant one, and that occurs on the time scale of an hour or so. And then if you care about vapor equilibrium, then on the time scale of many days, eventually that will be achieved. But the point is, it's really up to you to figure out what the appropriate time scale is for your experiment and make sure that you construct the experiment accordingly. Now, this concept of equilibrium relates to another concept called ergodicity. This was introduced by Boltzmann, and in probability theory, an ergodic dynamical system is one that has the same behavior averaged over time as averaged over the ensemble of all the system states in its phase space. So in other words, if a system is ergodic, that ergodicity implies the time average of some property P is equal to its ensemble average. And this equation shown here shows the time average on the left with the overbar indicating a time average, and then the ensemble average on the right with the angle brackets. Now, what is a time average? A time average means that you have a particular sample, let's say a sample of glass, and then you measure the same properties repeatedly over time and do some statistics on those time domain measurements, including calculating the average, and that would get you the average property value. The ensemble average is what if you were to prepare a large number of nominally identical samples. So in the case of glass, what if you make the same glass chemistry, you put it through the same type of thermal history, and you've made, say, 30 different samples, and you measure all of those samples and calculate the statistics, including the average. And that average would be the ensemble average. If the system is ergodic, then the time average would be equal to the ensemble average. If the system is non-ergodic, which as we will see is the case for glass, then the time average is different than the ensemble average. Now, this definition of ergodicity is not to be confused with the ergodic hypothesis. The ergodic hypothesis states that a system will become ergodic in the limit of long time. So even the glassy state as a non-ergodic state, if you wait in the limit of infinite time for it to fully relax to the supercooled liquid state or for it to crystallize, then it will become ergodic. And that is the crux of the ergodic hypothesis. So when we think about some of the basic physics of the glassy state, you're well familiar now with the volume temperature diagram here, so I'm not going to go through that again in detail. If you need a refresher on that, please go back to chapter 2 and those corresponding lectures. I think it's lecture 3. But one of the things, some of the things that we've learned about glass is that it's often defined by what it is not, as opposed to what it is. Since the structure of glass is frozen in from the supercooled liquid state, it has a non-crystalline structure. Because it is out of equilibrium, it is non-equilibrium from a thermodynamic point of view. From a kinetic point of view, it is a non-ergodic system, and I'll explain more about that in a moment. But another thing that we're going to cover in this chapter too a bit later is that the relaxation behavior of the glass from its non-equilibrium state towards equilibrium, that relaxation function is inherently non-exponential. And so we're going to cover each of these things in chapter 13. And one of the things that makes glass so interesting is because it is non-equilibrium and non-ergodic and non-exponential. The physics of glass has intrigued condensed matter physicists for a long time. And in fact, P.W. Anderson, the Nobel Prize winner in physics from 1977, has this quote saying that the deepest and most interesting unsolved problem in solid state theory is probably the theory of the nature of glass and the glass transition. This could be the next breakthrough in the coming decade. This was published in a paper in Science in 1995. We've made a lot of progress in understanding since then, and I will try to summarize some of those key details. But first, I need to introduce the concept of a Deborah number because this relates directly to the concept of ergodicity and will help us to understand why it is that a glass loses its ergodicity. So the Deborah number was defined by a physicist, Reiner, and it was named in honor of the prophetess Deborah, who in the Old Testament here, Book of Judges, chapter 5, verse 5, depending upon the translation, she says something like, the mountains flowed before the Lord. And the idea here is that if we go hiking on the mountains or skiing on the mountains, we do so with the implicit understanding that the mountains are not going to flow under our feet. And that is because we observe the mountains on a very short time scale compared to the time scale that is required for the mountains to flow. Mountains do indeed flow. That is a scientific fact that has been established over the past decades, but that flow happens over geological timescales. This is happening over tens or hundreds of millions of years or billions of years. And those timescales are not directly accessible to us as humans because we cannot observe on those timescales. However, if you were the Lord and could observe this on a geological timescale, you could see, in fact, that the mountains do flow. So the Deborah number, D, is defined as this ratio between the internal relaxation timescale of some process of interest over the external observation timescale. In other words, how long does it take for a process to occur divided by how much time do you actually have to observe it? And if we are trying to directly observe the flow of mountains, we are observing the system on a time scale of hours, days, years, but it is flowing on a time scale of many millions of years. And that means that the numerator is a lot bigger than the denominator in that case, and that gives the Deborah number greater than 1. Now, how does this apply to the glassy state and the glass transition. If we go on the left here, this is a simplified version of our volume temperature diagram. It's also an enthalpy temperature diagram because they scale in a very similar way. And if we start off at high temperatures and high volume or enthalpy in the liquid state, the kinetics of the flow behavior are very fast. Liquids can visit different configurations in the system and transition among different configurations on a very short time scale. And so this internal time scale is small compared to the external observation time scale, which means that the Deborah number is less than 1. And that implies ergodicity. That implies that the system is ergodic because any of the time average properties that we take are going to be done for the fully equilibrated system. And so if you compare the time average of properties to the ensemble average, you would get the same number. Now, what happens as we cool the liquid and get into the supercooled liquid state is that the kinetics become exponentially longer. So the viscosity of the system is increasing by orders of magnitude, and eventually the time scale of the relaxation process becomes of the same order as our observation time. So if we define an observation time as being, say, 1 hour, and the internal relaxation time is also 1 hour, then the Deborah number would be equal to 1. And when that happens, we get this breakdown of ergodicity because our time scale is starting to become longer than the time scale that we have to observe it. This is a continuous process because the time scales are continuously increasing for the supercooled liquid as it is approaching the glass transition. And then as it continues to cool, the kinetics are becoming exponentially longer and longer again. And then this numerator here, this internal time scale, becomes significantly longer compared to the external observation time. So we're still observing this on a time scale of hours, but it's requiring years or thousands of years or millions of years for the relaxation to occur. And therefore, the Deborah number is greater than 1, which implies a non-ergodic system. So the glass transition is, at its most fundamental level, a transition from an ergodic to a non-ergodic state. The glass transition range represents the range where there is a continuous breakdown of ergodicity. It is continuous because it is not a thermodynamic phase transition, as we know. It's because the timescales of the kinetics are continuously increasing. So in the glassy state, if you were to do a bunch of measurements over time, because of the glass relaxing over time, you would get different values compared to, or because of the glass being frozen in over time, you would have frozen in configurations. Whereas if you were to do the same type of measurements from an ensemble average sense, you will see configurational changes because the configuration that each piece of glass gets frozen into involves a random component. So there will be fluctuations over ensembles that are not observed over time because the time scale of doing the measurements is so much shorter compared to the time scale that is required for relaxation. So glass is an inherently non-ergodic system. And in fact, the glass transition involves imposing a kinetic constraint onto the system, which leads to this breakdown of ergodicity. Because of the kinetic constraint that gets imposed onto the system at the glass transition, there is a loss of the configurational degrees of freedom. That means that there's also a loss of the configurational contributions to thermodynamic properties such as heat capacity, coefficient of thermal expansion, and entropy. This also involves a falling out of equilibrium because we're not giving the system enough time to achieve equilibrium. So the liquid to glass transition going from the right here to the left involves imposing that kinetic constraint because you're not giving the system enough time to find equilibrium. You lose all the configurational degrees of freedom and the thermodynamic components that correspond to those configurational degrees of freedom. The opposite process of the glass transition is relaxation. Relaxation involves going from the glassy state to the liquid state. Relaxation involves a spontaneous lifting of the kinetic constraint, in other words, a restoration of ergodicity over an appropriately long time scale. As this is happening, the system is allowed to explore configurational phase space, and eventually we achieve thermodynamic equilibration as those new configurations are explored. And as in anything with material science, there are two factors that govern this relaxation process: kinetics and thermodynamics. Now, one of the most important theoretical descriptions of the glass transition is due to Frank Stillinger, who proposed this concept of potential energy landscapes and inherent structures. The idea is that any system is composed of n number of atoms, and each one of those atoms would have a position vector that in three dimensions would have an x, y, and a z component. And for any combination of these position vectors, so take n atoms and put them in any position that you want, there is some associated potential energy that corresponds to that configuration. Now, there is a minimum potential energy that would correspond to the perfect crystal, and all of the other structures that are not the perfect crystal would have a potential energy that is above that. And so that is this upper equation here, with the left-hand side is representing the potential energy landscape. And the reason it's called a potential energy landscape is that the potential energy is going up and down depending upon the particular configurations of the system. A kind of one-dimensional picture of that is shown here. Some configurations are favorable. They are correspond to local minima in the potential energy landscape. Each one of these local minima is a mechanically stable configuration of atoms, because if you were to perturb this in any direction, the direction of lowering the potential energy landscape, or the potential energy, would be going down into that particular minimum. Now, the potential energy landscape in reality is not one-dimensional. It is, in fact, 3n-dimensional, because every one of the n atoms has three translational degrees of freedom, x, y, and z. And so the number of possible dimensions to vary with respect to the atomic configuration is 3 times n, because each of the x, y, and z coordinates of each of the n atoms can be varied independently of each other. So this potential energy landscape is actually a 3n-dimensional hypersurface with a lot of mountains and valleys. And what Stillinger proposed is that we could take this continuous potential energy landscape and identify these local minima in the landscape, these local potential energy minima. He called them inherent structures. These mechanically stable configurations of atoms that correspond to local minima are called inherent structures. And then if you go up the potential energy landscape in any dimension, there would be a whole kind of segment of the landscape where if you were to go downhill in energy, it would all drain to that same minimum. And the volume of the potential energy landscape that drains to a particular minimum is called a basin. And so there's one basin for every inherent structure of the system, and all of the energy landscape can be divided into these disjoint basins. The other thing to note is that in between basins, there is a transition point, which is basically an activation barrier that needs to be overcome for the system to transition from one basin to the neighboring basin. And kind of the fundamental postulate here of Stillinger's description of the potential energy landscape is that the kinetics of the system and the thermodynamics of the system can be divided into vibrational components, which represent vibrations within a basin. So these would be vibrations about a given inherent structure within a basin. And then configurational contributions that represent moving from one basin to another basin. So overcoming one of these activation barriers and making an interbasin transition that is a configurational change. So we've got vibrations that occur within the basins, and then configurational changes that occur from basin to basin. And all of our thermodynamic properties and our kinetics can be described in terms of these vibrational contributions and configurational contributions. Now, if we are at equilibrium and we have an ergodic system, that means that the system is able to freely explore the potential energy landscape to find its equilibrium. What if we have a broken ergodic system? From the point of view of an energy landscape, broken ergodicity implies that we are trapped in some subset of the potential energy landscape. And the physics of broken ergodicity was initially developed by Palmer back in the early 80s. And Palmer considered, what if we had an energy landscape that's like this, where there's a group of basins here with relatively small barriers separating them, another group of basins that also has a small set of barriers, but then a larger barrier in between that two sets. And Palmer considered that this first group here could be labeled as a component, component alpha, and the second group is labeled as component beta. And he considered, what if our observation time is much shorter than the time that's required to overcome this large barrier? So if the observation time is much smaller than the time required for an intercomponent transition, Palmer assumed that we have confinement, meaning that if the system happens to be in component alpha, it is stuck in component alpha and unable to go over the barrier to component beta. In the same way, if the system happens to be in component beta, then it is stuck there and unable to go over this large barrier to get to component alpha. So Palmer's first condition is that of confinement. Palmer's second condition is called internal ergodicity. And this is because the observation timescale is assumed to be much longer than the timescale of the basin transitions within the component. So because of the much lower activation barriers within the component, these transitions can occur rapidly, and therefore you can get a localized equilibration within the component. And this is Palmer's condition of internal ergodicity. So ergodicity applies within a component, but it doesn't apply between components. And that's why he called this broken ergodicity. So ergodicity within the component is good, but we have confinement within the components. And what this means is that if you have any property of the system, let's suppose the entropy of the system, that there is a certain entropy that is associated with a system being in component alpha, that's S alpha. There's a certain entropy that is associated with the system being a component beta, which is S beta, and it can be any property. And then the expectation value of the entropy would be the weighted average here of the entropies of being in either of those components, weighted by the probability of being in that component. So if there's a probability P alpha of being in component alpha, and we know if we happen to be there that we are stuck there, its contribution to the entropy is P alpha times S alpha, and then there's a probability of being trapped in component beta, which is P beta, times the associated property value. And so if you take that weighted average, you will get the expectation value of the property. What are some of the implications of Palmer's approach to broken ergodicity? The breakdown of ergodicity for any system, including that which occurs at the glass transition, necessarily results in a loss of entropy. And that is because the system is unable to explore all the configurations that it would be able to access in an ergodic system. For a non-ergodic system, we are constrained to a subset of the energy landscape, and therefore not all of the configurations are mutually accessible. So there is a loss of the configurational entropy of the system and a corresponding increase in the free energy of the system. At the same time, that doesn't change the internal energy or the enthalpy because the math works out in that case to be the same for the ergodic and their non-ergodic system. So there's a loss of entropy, an increase of free energy because of that, but no change of the internal energy or enthalpy. And that's exactly what we see in our enthalpy temperature diagram, just like in the volume temperature diagram. When the glass transition occurs, there's no change in the enthalpy or the volume. It's just a gradual freezing in. Palmer's two conditions for metabasin partitioning are confinement which means no transitions between metabasins, and internal ergodicity, which means that there are fast transitions within the metabasins. And this satisfies the principle of causality, which is a thermodynamic principle that says that properties can only be affected by the microstates that are actually visited by the system. Properties cannot be affected by kind of microstates that are hypothetically available, but not actually visited. What are some of the limitations of the Palmer approach? In real glasses, it's often difficult to partition the potential energy landscape since you don't necessarily have this large barrier separating regions with relatively small barriers. That particular topography of the energy landscape need not occur. Also, Palmer's condition of confinement is really too strict because at any temperature above absolute zero and for any non-zero timescale, there's always some finite probability of being able to overcome a large barrier. That probability may be small, but it's still finite. So the condition of confinement is never strictly true unless you have the limit of absolute zero temperature or zero observation time. And the other issue is that within the glass transition range, the kinetics there are really too fast to assume confinement and too slow to assume ergodicity. And that is because the Deborah number within the glass transition range is of the order of 1. And Palmer's approach really just applies to the non-ergodic system at temperatures well below the glass transition. So there are some major shortcomings here to Palmer's approach that need to be addressed. And the way that we do that, the way that we describe the thermodynamics or statistical mechanics of a realistic glass forming system is through a generalized theory called continuously broken ergodicity. So with continuously broken ergodicity, which was published here in Journal of Chemical Physics in 2007, we can take any type of potential energy landscape with any topography, and this is fully applicable to everything from fully ergodic to fully non-ergodic systems and everything in between. And we do this by defining two types of probabilities. There is first the basin occupation probability, the P sub i's. This tells you what is the probability of if you take an instantaneous snapshot of the system, that you would find the microstate in I, for example. If you're in this basin I here, that probability is Pi. If you take a snapshot of the system, the probability of finding it in this other basin J is Pj. That's the first type of probability, and for a non-equilibrium glass, that depends on the entire thermal history of the system. The temperature is a function of time. Now, the second type of probability is a conditional probability. This is Fij. The two indices are telling you what is the conditional probability if I start in basin I, that after I propagate the system over the observation timescale T observed, that I will end up in microstate J. So Fij says, okay, if I start in basin I, what's the probability of ending up in basin J after the observation time? And if we have the limit of zero observation time or zero temperature, that means no kinetics can occur. And in that case, the conditional probability is reduced to a Kronecker delta function, delta I comma J, which means that in the limit of zero time or zero temperature, whatever basin you're in, that's where you're stuck because no kinetics are allowed to occur. So with this conditional probability Fij, this gives the probability of transitioning to microstate J after an initial measurement or an initial observation in microstate I, and then evolving through an observation time T observed. With this formulation, we can define a conditional entropy. The conditional entropy, if you have started in microstate I, would be S sub I. This is the entropy for starting in microstate I, and this is just the Gibbs formula using the conditional probability. So it's minus Boltzmann's constant times the summation over all the possible microstates J, and then using the conditional probabilities Fij for that observation time times the logarithm of those conditional probabilities. And this gets you the conditional entropy if you started in microstate I. To get the expectation value of the entropy or any property, then we do the weighted sum of that using the base and occupation probabilities. So we sum up over all the possible starting configurations and take the property value, if you started there, S sub I, multiply by the probability E sub I, and that gives you the expectation value. Now, some of the implications of continuously broken ergodicity are that this formula simplifies to the Gibbs entropy for an ergodic system, because for an ergodic system, the conditional probabilities approach the equilibrium probabilities. If you have if the ergodic hypothesis is true, then it doesn't matter where you start, because in the limit of infinite time, where you end up is just governed by the equilibrium distribution. So this becomes the Gibbs entropy for an ergodic system. It also simplifies to the Palmer approach for the special case of discontinuously broken ergodicity. In other words, if you assume that Palmer's conditions of confinement and internal ergodicity are true, and apply that to this formulation of continuously broken ergodicity, then you can recover Palmer's approach as a special case. This also means that entropy is zero in the limit of zero temperature or zero observation time. This is consistent with the third law of thermodynamics. It's consistent with Boltzmann's notion of entropy as the number of microstates that are averaged over to yield a given macrostate. And it is consistent with the principle of causality, since the properties of the system can only be affected by the microstates actually visited by the system. And another implication is that ergodicity is restored in the limit of infinite temperature for any, in the limit of infinite observation time for any non-zero temperature. So all of our normal thermodynamics and statistical mechanics for equilibrium systems can be recovered in that ergodic limit. All right, that was your introduction to the thermodynamics and statistical mechanics of the glass transition and relaxation. In the next lecture, we are going to take a closer look at the concept of fictive temperature and try to understand what are different interpretations of fictive temperature, because different people may mean different things. And we're going to find out more next time. All right, thanks everyone. If you have any questions, please let me know. Thanks for watching.